Hello everyone, in this video we will cover the section 2.5. In this section we will see matrix factorizations, the Lu factorization. A factorization of a matrix A, m by n, is an equation that expresses A as a product of two or more matrices, namely we find the factors of the matrix A such that the multiplication of them will give the matrix A, like the product of the matrix A1 times A2 times A3 blah blah an. Okay, we can have two or more matrices in this product and A1, A2, A3 blah blah an are called factors of the matrix A, whereas matrix multiplication involves a synthesis of data, namely the matrix multiplication combines the effects of two or more linear transformations into a single matrix. The multiplication combines two separate information, but matrix factorization is the opposite situation, namely it is an analysis of data. The Lu factorization described on the next few slides is motivated by the fairly common industrial and business problem of solving a sequence of equations all with the same coefficient matrix, like this sequence 1, ax is equal to b1, ax is equal to b2, blah blah, ax is equal to bp. Okay, bp. P is an index here, not the product of p times b. Namely, the Lu factorization can be useful when we solve a sequence of systems like this one. To solve x for each one will be very easy by using the Lu factorization of the matrix A. When A is invertible, one could compute the inverse of the matrix and then compute these ones. However, it is more efficient to solve the first equation in the sequence by row reduction and obtain the Lu factorization of A at the same time. Thereafter, the remaining equations in sequence are solved with Lu factorization. Okay, this is more efficient method for solving the system written here. And also the Lu factorization is useful when computing the determinant of this matrix, and it is a case that when we find the inverse. At first, assume that A is an m by n matrix that can be row reduced to echelon form without row interchanges. We don't use this operation when we find echelon form of the matrix. Okay, you know we have three operations: replacement, interchange, and scaling. We don't use the second one to find the echelon form, and we assume this fact for the matrix A, which is m by n. Then A can be written in the form A is equal to L times U, where L is an m by n lower triangular matrix. This is important. Lower triangular matrix, like this one. As you can see, we have a lower triangular matrix here. On the main diagonal, we have a special condition here. All entries on the main diagonal are ones. as you can see. Since we have a lower triangular matrix, all entries above the main diagonal will be 0, as you can see, and other entries can be any number. And U will be the echelon form of the matrix A. U is n by n echelon form of the matrix A. This is lower triangular matrix. Lower triangular matrix, and this is echelon form. You know how you can find the echelon form. And so we will learn how we can find the entries of the lower triangular matrix when we use the row operations to find the echelon form of the matrix A. The first matrix is m by n matrix, and you know the echelon form is m by n matrix, and the given matrix is also m by n, you know. The matrix L, the lower triangular matrix L, is invertible and is called a unit lower triangular matrix, since we have 1 on the main diagonal for every entry. Okay. Before studying how to construct L and U, how to find L and U, we should look at why they are so useful. When A is equal to L times U, we have a matrix multiplication here. The equation Ax is equal to B can be written as L times Ux is equal to B. Instead of A, we write the factors of the matrix A, Lu. And we have associativity property for the product of matrices. We consider X as a matrix. So we can write this thing, okay? Ax is equal to B becomes in this form. Writing y for U times X, we can find X by solving the pair of equations written here. So writing y for U times X, we have Ly is equal to B, and we know y is equal to Ux. First we find y from the first equation, and writing this into the second equation, easily you find the vector x. Each equation is easy to solve because L and U are triangular. Directly we find the components of the unknowns, which are y and x. L is lower triangular, U is upper triangular normally. For example, use the Lu factorization of the matrix A written here. Actually it is given already. The first matrix will be L, the second matrix is U, and we will use this factorization to solve the equation Ax is equal to B, where B has the components minus 9, 5, 7 and 11. First let's find namely let's learn how we can construct the matrices L and U. So we have here the matrix A, example 1, the matrix A is written as 3 minus 3, 6 minus 9, minus 7, 5 minus 4, 5, minus 2, 1, 0, minus 5, 2, 0, minus 5, 12. We have 4 by 4 matrix, and our aim is to solve the equation written here. X is equal to b, and b has the components minus 9, 5, 7, and 11. Okay, so we want to find the Lu factorization of this matrix L times U. So we start with the first pivot position of the matrix A. When we look at the matrix A, first pivot position is located in the first row, and this is the leftmost non-zero number, which is actually 3. And to find the echelon form of this matrix, we have to find 0 for all entries in the first column except the pivot position. In the minus 3 should be 0, 6 should be 0, and minus 9 should be 0. And for the first column of the matrix L, which is lower triangular matrix, after finding the first pivot position, so we divide the first pivot position by a number to get 1, which will be 3, as we can see. When we divide the first column of the matrix A, since we have the first pivot position in this column, so to find 1, we divide this column by 3. So we obtain 1 for the first entry in the first column. We have minus 1 for the second entry. Similarly 2 and minus 3. So this is the first column of the matrix L. Okay, so to find 0 for minus 3, 6, and minus 9, we do row operations. We can write R2 is replaced by R2 plus R1, and we don't use interchange operation when we find the echelon form of this matrix. We don't use the second operation, row operation. You should be careful. R3 is replaced by R3 minus 2R1, and the last row is replaced by R4 plus 3R1. So the matrix becomes 1, 0, 0, 0, minus 7, minus 2, 2, R2 plus R1. So we have minus 2, minus 1, 2. And the third one, R3 minus 2R1. So we have plus 10, 4, and minus 9, I guess. And for the last one, 3R1 minus 21, 21 plus 5 becomes minus 16, minus 6, minus 5 becomes minus 11, Plus 6 plus 12 becomes 18. Okay, this is the first pivot position, and now we are finding the second pivot position, which is located in the second row. The leftmost non-zero number is -2, and before the row operations we will construct the second column of the matrix L. You know, we have triangular matrix. The first entry will be 0, the second entry will be 1. To get 1 for the pivot position -2, we divide this number by -2, and we are not interested in -7 since we have 0 already from the definition for this entry. And after dividing this column exact -7 by -2, we get -5 for 10, and for -16 we have 8. So now we can do the row operations. R3 we should get 0 for 10. R3 should be replaced by R3 plus 5 R2, and R4 is replaced by R4 minus 8 R2. So we have from here 1 0 0 0 -7 -2 2 -2 -1 2 0 0 4 becomes, so we have 5 R2 -5 plus 4 becomes -1, 10 -9 becomes 1, and yes, -11. So we have -8 plus 8 -11 becomes -3. -16 plus 18 becomes 2. Okay. Before the row operation, again we are finding the third pivot position. This is the first pivot, second pivot, and this is the third one. And we have 0 0, -1 will be 1. To get 1 we will divide this number by -1 by itself, so we have 3 for the last entry. And to get 0 for -3, R4 is replaced by R4 plus -3 R3. Therefore we have 1 0 0 0 -7 -2 0 0 -2 -1 0 2 2 1, so -3 plus 2 becomes -1, and this is the matrix U. This is in echelon form, and the last row will be 0 0 0 1 always. So this is the matrix L, lower triangular matrix, and this is the echelon form. So the matrix A becomes the product of them. You can check yourselves. So now we can solve this equation by using the Lu factorization. So it becomes L times Ux is equal to B. Instead of A, we write the product written here. And from here we have Ux is equal to Y by writing Y for this one. And Ly is equal to B. Ly is equal to B. You see the matrix L. So we know the components of the matrix, the vector B. So writing again 1 minus 1 2 minus 3 1 minus 1 2 minus 3 0 1 5 0 1 minus 5 8 0 0 1 3 0 0 1 3 0 0 0 1. Zero 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 one, and we write B. This is the augmented matrix of this equation. B has the components minus 9, minus 9, 5, 7, 11, 5, 7, 11. So using the first row, we have 4 components for y, y1, y2, y3, and y4. Okay. So from here we can find directly the variable y1 because we have just a single non-zero number in the first row. So from here we find y1 is equal to minus 9, and from the second row we can find y2. Since y1 is equal to minus 9, from the second equation we have minus y1 plus y2 is equal to 5, and from here y2 is equal to, writing minus 9, we have plus 9 for here, so y2 becomes minus 4. And from the third row we have 2 y1 minus 5 y2 plus y3 is equal to 7. So from here y3 is found as 5, writing minus 9 and minus 4 in this equation. And from the last equation, from the last row, you have 3 minus 3 y1 plus 8 y2 plus 3 y3 plus y4 is equal to 11. So we have y4 is equal to 1, writing them here. And then after finding the variable y from this equation, so we can find x easily. We know u written here, so writing here the augmented matrix of the first one, this one, 1 0 0 0 minus 7 minus 2 0 0 minus 2 minus 1 minus 1 0 2 2 1 minus 1, and it is equal to y Namely, we have minus 9, y2 is minus 4, y3 is 5, y4 is 1, and from here the first column is corresponding to x1, the second one is x2, x3 and x4. Therefore, from the last equation, last row, we have minus x4 is equal to 1. We don't have free variables since we have pivot position in every column, as you can see. So x4 is equal to minus 1, and from the third row we know minus x3 plus x4 is equal to 5. So x3 is written as minus 6, and from the second one we have minus 2x2 minus x3. The coefficient is minus 1, therefore we write minus x3 plus 2x4. So from here x2 becomes 4, and from the first one, from the first row, similarly you can find x1, which will be equal to 3. Therefore the solution will be, we have a unique solution since we have a pivot position in every column, and this is a square matrix, so it means that it is an invertible matrix. Therefore the solution will be unique by the invertible matrix theorem also, and we don't have free variable, which means also we will have a unique solution. So we have 3, 4, minus 6, minus 1. This is the solution of the system by using the Lu factorization. Okay, Lu factorization. You see 3, 4, minus 6 and minus 1. So algorithm for and Lu factorization reduce the matrix A to an echelon form view by a sequence of row replacement operations if possible. Place entries in L such that the same sequence of row operations reduces L to the identity matrix. For example, there is another one. Find the Lu factorization of this matrix. We have now 4 by 5 matrix. We have 4 rows and 5 columns. This is not a square matrix. In the previous example, we have had a square matrix, which is 4 by 4. So since A has 4 rows, the matrix L should be 4 by 4 because M is equal to 4 and N is equal to 5. If you remember the formula, the lower triangular matrix should be M by M matrix. Therefore, M is equal to 4. So we have 4 by 4 matrix for L. And U is the echelon form of this matrix, so it should has the same size, 4 by 5 matrix, you know. Our aim is to find the factors of the matrix L, matrix A. Lu factorization L is 4 by 4 and U is 4 by 5. Therefore we have we can apply the matrix multiplication since we have the common number, as you can see. Okay, first we need to find the first pivot position of the matrix A. The first pivot position is 2, which is located in the first row always. So we should get 1 for 2. To get 1, we divide this number by 2. And also we apply the same operation for the other entries in the first column. We divide 2 by 2, we have 1, as you can see. Minus 4 becomes minus 2, we divide by 2. 2 becomes 1 and minus 6 becomes 3, as you can see. This is the first column of the lower triangular matrix L, and we know always we have 1 on the main diagonal and all entries will be 0 above the main diagonal, as you can see. So our aim is to find the entries located here. Okay, we have 3 entries that we don't know now, for now. And similarly, we do row operations to get 0 for minus 4, 2 and minus 6, as you can see. And then you can write yourselves the operations here. We find the second pivot, which is 3, okay, after the row operations. And similarly, we should get 1 for 3, and we apply the same operation for other entries below the pivot position, namely which are minus 9 and 12. Therefore, when we divide by 3, we get minus 3 and 4. Minus 3 and 4. Okay. After row operations again, to get 0 for minus 9 and 12. And you see we have again 0 here. The first pivot position, the second pivot position, and we look at the third row. The next pivot will be 2, which is the leftmost non-zero entry. To get 1, we divide by 2. Therefore, this one will be 2. We have 1 here, as you can see. And after the row operation, the last pivot position will be this one. Okay, this one, and this one. So the first one is corresponding to x1, x2, x3, x4 and x5. x1, x2, x4 and x5 are basic variables, and x3 is a free variable. When we solve a system, if its coefficient matrix is the matrix A, this is the echelon form, which is U. Okay, x3 will be free variable, namely we have infinitely many solutions, okay, for the system, infinitely many solutions. So you see the matrix L here, like this one, minus 3, 4, 1, 2. An easy calculation verifies that this L and U satisfy this equality. When we multiply the matrix L and the echelon form of A, we get itself. Okay, this is the method, this is the operation for finding the L and U, which are the factors of the matrix A. Okay, thank you very much for your listening.